Greetings. Today, the topic in this video that I'm going to discuss with you guys is CPU scheduling. The host of this video is myself. My name is Sahzeb Rafi and my groupmate Subhan Suleiman. Now, starting off, we are going to discuss the what, why, and gradually to the how of CPU scheduling. Starting off with the introduction. Now, first, whenever we perform a click or any other activity in our computer, we are actually creating a process which is given to the CPU as input. And the work of the CPU is to process that process. A CPU can get multiple, even hundreds of processes per second. So what it actually does is it put them in a job queue. A job queue is basically a simple queue structure, and it placed all the processes that it is receiving in them, and then the second process is the second work for the CPU is to decide some criteria on which it will decide which process to execute first and which to execute next, and when to stop a process and when to resume a process. So, like this picture on the right, here there is a job queue and then there is a ready queue, and up, whenever process in a ready queue, it is passed over to the CPU, and CPU performs execution, and that the process is complete. So, moving on, we're going to discuss why of CPU scheduling. Why do we need CPU scheduling? The reason is to increase throughput. The throughput is the number of jobs a CPU is performing in a unit time. For a CPU, a unit time can be a millisecond or even smaller. It depends on the CPU architecture. So we want to maximize our throughput. So as we want as many job done as possible in a unit time of a CPU. And also we want to minimize the turnaround time. Now, the turnaround time is the time when a process comes into the CPU till time when it leaves the CPU as because it is complete. So we want to minimize the time a process is within in the queue, and and we want it to minimize so that a process is done as quickly as possible. It doesn't have to wait for the CPU, and in the end we want to utilize our CPU the max. Because in unit time of CPU is very small, they are very small in time interval where the CPU is idle. We want to minimize those time intervals as little as possible so that we can utilize our CPU at its max and we get most work out of it. And so this will eventually increase the throughput, which is the reason why we're doing CPU scheduling. So before I tell you how we are going to perform CPU scheduling, I mean what criteria we're going to discuss, before that, we are going to introduce some terminologies so that you can know about them, and that will help you better understand the rest of the video. The first is arrival time. Now, this arrival time is the time a process enters the job queue. This is very simple. And the next is the burst time. Now, this is different because this is the time that a process will use the CPU, meaning it is a time where that CPU will take to complete this process. Now, the calculation of this burst time is done by the process itself, and it is not always accurate. It is done on the trends. It the CPU, the process itself calculates how much time it took before the last time the same process came, and eventually it creates a graph and decides the burst time. It's not always accurate. And the next is the completion time. It is a time when the process is complete, and meaning the CPU has performed the process and now it's done. Some other terminologies are turnaround time. Now, this turnaround time also includes the burst time and all the other waiting time and response time, meaning all the time the process was in a job queue, it was not being done, and all the time it was being performed, all that time accumulate to turnaround time. In the waiting time, it is all the time it is in the queue, it's not being processed, it is waiting for its done, it is in the waiting state and area the steady state, it's not being processed at that time. All that time together is waiting time. And the next is the response time. It is a delay of time where it has to wait for the response also. So Now that we have discussed the terminology, we're also going to discuss some challenges that we will be facing CPU scheduling. So that now the first is conveyor effect. Now the conveyor effect is when a very large process game, meaning it is going to take a lot of CPU unit times. So what happens if we send it first, all the other process which might be 1/10th or even 1/50th of its actually burst time will have to wait for a very long time. This is conveyor effect, where a large process holds the CPU for a very long time and other processes have to wait for a very, very long time. On its opposite, starvation, which it is a complete opposite of which, in which the very, very small processes comes very small sometimes keep on coming and they keep on being evaluating, meaning there's some criteria in which we are processing the shortest first. So what happens if there is a very large process, it will have to wait a very it will have it might have to wait for a very long time and might be stuck there because there are other processes who have comparatively less burst time than it, and they will have to wait for a very long time. Now we are going to discuss the how of the CPU scheduling. How are we going to do this? So as we have discussed, the CPU itself puts them in a job queue, but it needs some criteria by which it will decide which process comes first, which comes next, which to hold, and which to resume. The first and the most simple is the first come first serve. First, I'm going to tell you about its properties, and then I'm explain how it works, so that you can understand it better. Thus, just for your understanding, it works in a linear manner. It follows the first in first out principle, meaning the first one that comes will leave the queue earliest. And this is used in batch system where all the processes are performed in sequential order. And what happens in batch system is we give CPU multiple jobs and perform that sequentially. Mean it took from list the first job, it completes it, then take the second job and completes it. Now, and also it is non-primitive in nature, meaning when it gets a hold of CPU, it will never voluntarily leave that CPU. That is what a non-primitive scheduling operating is. We're going to discuss how this actually works. So, as I've told you earlier, that CPU has a job queue where it keeps all the incoming processes. So, what FCF does is like a like as just said, it follows the FIFO principle, meaning that the first process that came will always execute first. So if there are three processes and they all came in increasing order, meaning the first came 5 minutes before the second come 5 minutes the third, so they all will be processed sequentially. The first will be executed first, the second will be executed second, and the third will be executed second, as they are placed in the queue. This is very simple. Now, we're going to discuss the advantages of first come first serve. The first is that it is very easy to implement, as it is simply just a queue data structure. The next is it is an equitable algorithm, meaning that it ensures fair allocation of resources. And the third is that it is used in batch system, like I discussed, where there are multiple jobs and the CPU performs each job sequentially. Now, there are also some cons. The first is, of course, conveyor effect, as it does not have any sophisticated criteria. The first come will also first step. So, if there is a process that has a very high burst time compared to other, maybe it is has 50th 50 50 times more than them. So, there will be no checking. It will be executed at its time, and the CPU will not consider other processes that are small to it but came late. This so convey effect results because a very large process came and it is being executed, and we are not considering other small that came, which might be 1/10th of it. The next problem is, of course, problem for IO processors. As we know, there are two types of jobs: the CPU job, CPU extensive jobs, and the IO bound job. IO bound job. Now, for this IO in our computers, we need immediate response to our IO response. So whenever we click enter, we want immediate response. Whenever we are typing, we want immediate response. So, but in FIFO, we have no priority for them. So they are taken as simple processes and are put in queue, and they have to wait for their turn. And this is it is Avanti, and it does not allow real time execution. After first comes up, I'm going to discuss round robin. Now, the first concept was non-primitiveness, meaning if a process get a hold of the CPU, it will not leave it. However, round robin is non-primitiveness, meaning it will have to leave the CPU non-voluntarily, even if it does not have to. The schedule will not allow it and will take the CPU back from it. So, the primitive nature and how this work is, it makes time slices, time intervals. It will give a certain time interval to process. After the time interval is complete, it will take the CPU back from it and then allocate the CPU to some other process and give it some time interval. This time interval can be between 10 to 100 millisecond and is fixed. So each process will get a fixed will get same time compared as the other are getting. Now this technique is time series technique where we give him time, give him some time after we take process from the CPU format, then give the CPU to the other process, give it some time, then take CPU back from it. Now, we're gonna discuss briefly its working. So what we do are we are gonna make some time quantums, and can be like I said, can be between 10 to 100 milliseconds, and we are gonna continuously be switching processes as soon as their time expire. So process one came, it is given 2 seconds. 1 second, 2 seconds. As soon as 2 seconds, we will take the CP format. No matter whatever it's doing, we will store all its states, and then we will go to the next process, and we will give the CPU to it. Now, and also 2 seconds. After 2 seconds, we will take CPU back from it, and then the third process. Say if they are third process, three processes, then the one process get 2 seconds, second, third, and then we go back to the first one. Then to second and third event, and eventually they will all finish. So say two, the process two gets done first, then the left are one and three, then the CPU will cycle between the one and third until they are both complete. This is it working. Now moving on, let's discuss the advantages of round robin. The first is fair allocation, as we are giving equal time to each process, and there is no other criteria. We are not putting any priority over anything else. And this also prevents starvation, because as I said, starvation is when us when many small processes are coming and a very large process has to wait a very long time because of some criteria. The criteria does not exist here, as we are providing equal slices of equal small slices to everyone. So everyone is getting the time, and it's like we are performing real time execution. The third one is time saving, like I discussed. We are getting real time execution. Now moving on, it has done some response like higher delays. The waiting and response time are higher due to short time slot. As they are very short time slot, so a process starts, a process starts, it gives a very small time, and then we have to switch, and there is also a delay, an overhead on on the switching. So there will be a lot of switching, meaning if we somehow have a very small time slot, this might become an issue because there will be so fast switching between them, and each process will be getting very small time. The other is higher context switch. Like I discussed, if as we decrease our time slot, the switching between the process, meaning the allocation from one CPU to another, will be happening very frequently, and there will and between the switching there is overhead, because when we switch, we store the previous values of the process and load the values of the new processes.